Wow, I have one student at 9 o'clock. I really drove everyone away last week. Well, it seems a bit silly to start with one student, so let's wait a little while longer. The lectures are meant to start at 9 o'clock, right? Not 5 past. You're going to get a private lecture. I hope you have lots of questions.
So you are here only for 2 weeks?
Yeah, so very strange. I'd already organised all this travel when I found out that I was meant to be involved in teaching this course, so I was only available, and so Sarah and I were split the roles. So, and it turns out, I thought it was going to be 3 weeks each, but it turns out that I'm away because I was going to teach week 12 as well, but I actually arrived back my flight lands at 9 o'clock on the Monday morning. So I'm not going to be here in time. But I'll be involved with all of the marking and all the rest of the whole of the Part A, the quantitative methods. Well, there you go. You have my record. First time I've given a lecture to one person. So I'm sure everyone is out there in the cloud watching live or not. 9 o'clock lectures. The modern 9 o'clock lecture. Okay, so this lecture we're going to talk about models and simulation and optimization. And basically, why do we make models? How do we evaluate them? So simulation is one way of making models. How do we represent reality? What kind of scenarios can we do? How sensitive are our models? And some other issues that come up when you're doing modelling. And then I'll talk briefly about optimization modelling, because that's what I do. Where we, instead of simulating decisions, we actually ask a solver to make good decisions for us. So it's a different kind of model. So the idea of this module is that you should understand the nature and use of models, why we build simulation and optimization models, what we use them for, and a little bit about scenarios and repetition and sensitivity. Yeah, and hopefully be able to build some simple models and use simulations to investigate simple scenarios and carry out some sensitivity analysis to look at how your models change if you change some parameters. All right, so let's talk about models and evaluation. So what's a model? Okay, so here is my huge interactive crowd. Which of those things are models, do you think? Is a fashion model a model? How about a road map? How about the road rules or a photograph, a sculpture? How about a scientific theory about something? A lab rat's a model? Sheet music? Is that a model of something? Painting or an organisation chart? So which do you think are models? Maybe everything. Give the man a prize. Okay, I mean, they can all be thought of as models. Look, they don't necessarily have to be models. So a fashion model is meant to be an idealised representation of the human body, right? A road map is clearly a model of the roads. It's not the actual roads, but it models how they connect and things like this. Road rules is a bit more interesting. Road rules is a model of how people are meant to interact on the road, right? So it's a model of interaction, unlike a road map, which is a more directly just a model of the roads themselves. A photograph. Well, a photograph you can think of as modelling reality, right? And similar, a sculpture could be modelling reality, although sometimes that doesn't make any sense, right? Sometimes a photograph is not modelling any reality, and a sculpture is not modelling anything real. Yeah. A scientific theory, that's clearly a model, right? That if we say this is the way things work, we're actually making an artificial assumption about how things work. It may or may not be accurate. Typically it's, right, scientific theories we try to be as accurate as we can be, but we know that we don't usually capture everything. So lab rats as themselves are not models, but they're used as models, right? When you have a rat in the laboratory, you're using its body. No, what I'm trying to think. I'm trying to think of its there's a word. I want operating system for humans. We're using its metabolic system basically as a model of life that we can try our drugs on and see how they behave, and then hopefully map that to humans later on. So we're basically using this organism as a model for a more complicated organism. So sheet music is also a model, right? So that's modelling music. It's not the actual music, but it's, if you want, a representation of what the music is. Certainly doesn't have all the information that the music has when it's actually played. So therefore, it's a model. A painting can be a model. If it's a portrait, you can understand that's clearly a model. Other paintings, of course, if it's a Mondrian, it's not so clear that's modelling anything. And finally, an organisation chart is a model. There you go. It's good. I started with a lecture with one person. I do believe the lectures start on the hour. I gave you 5 minutes, which would be when they start at Melbourne University. All right, so we're talking about models. Just to give you a hint, we're going to talk about models, simulation and optimisation. Okay? So it turns out that all these things up here are models, right? A model is basically a representation of reality, right? Something that represents something in the real world. Yeah, but it abstracts out key features. So if you think about a road map, right, it's not the same as the road. It doesn't tell you where the potholes are, right? But it tells you a lot about what you need to know about a road. It tells you the connectivity of the roads, and it can tell you distances and all kinds of things, right? So a road map is a great model of the road. Okay. And the good thing about models is if we look at models, then they start to reveal similarities. So if we think about all these kind of models that we might make, so modelling an epidemic, right, or modelling fire spread, or modelling a nuclear chain reaction, right, so that's right down from epidemics might be at the world level, and the nuclear chain reaction might be down in little microns, looking at individual atoms, yeah. All of these model the same thing. They all model basically a spread of percolation across networks, right? So if you think about how epidemics work, you know, I have the cold and then you have the cold and then your friends get the cold. It's something that's percolating across networks. Same happens in a nuclear chain reaction. One atom splits, sends out some alpha particles. It hits another atom, that splits, and you can see it percolates across. Right? And if we're modelling nuclear chain reaction because we want to get to critical mass, exactly critical mass is the thing where suddenly everything gets hit and everything splits. So, all of these kind of models, which look completely different, right, are really examples of very similar things. The percolation of some kind of behaviour across a network. All right. So as you said, a model is a representation of the real world. And best example, that's a road maps and guinea pigs again, like lab rats as an example of a metabolism we're going to use the guinea pig's actual metabolism as a model for a more complicated thing, like a human's metabolism. We're going to test our drugs on them, right? And we know that there's differences in their metabolisms, but we'll learn from how the drugs work on their metabolism, and then we use that to give us evidence to eventually guide to clinical trials where we'll actually use humans, for example, for drugs. Okay, so what do we do with models? There's quite a few different things we can do with models. So we can use them to predict, right? So if I have a model of how stock prices are going to move, then I should be a very rich man, if I'm correct, right? This is the kind of the golden ticket. If you can forecast how stock prices are going to move, then in fact you're going to be very rich. And we came close to that, and that shows you another example about modelling. Actually, I'll divert. So there was what's called the Black-Scholes model of risk. Okay, so this is a very important model of how to trade off basically risk versus volatility. And these guys, Black and Scholes, who are economists, came up with this model of how to evaluate risk, and then they basically built a stock basically options system where they would buy stocks and options in order to make sure that they took account of risk, and they basically made a profit. And so for like 15 years in a row, they had a very, very impressive record of making profit above the market rate. And in fact, they were very, very successful. They had this model and it seemed to work, and so everyone jumped on the bandwagon, and more people invested with them, and more people invested with them. And what happened was their model broke, because now actually they were so much of the stock market that the stock market didn't act how it used to, right? And in fact, they lost $1 trillion. A trillion with a TR. Not $1 billion, $1 trillion. Okay? And basically the whole stock market would have gone, except the US government basically forgave them the debt. Right? So you can read up about Black-Scholes. It's very interesting, and it's very, if you get the right documentaries, it's really good, because one of them, I can't remember, is being interviewed. He's lost $1 trillion of other people's money, and he's being interviewed on the balcony looking over his ballroom. All right? So clearly he didn't lose all his money, but it's very, very interesting. Okay, so planning and forecasting, that's exactly what a lot of people, and stacks of people in the stock market doing that, right? And you have more or less success. But actually, mostly success in the stock market is about insider trading. Okay, another thing you can do with models is you can explain things. So if you have an accurate model of what's going on, right, then you can make some statistical hypotheses about it, and you can test it. And finally, and I think the most interesting thing for model, is that when you have a model of something, then you can start to control it. So you can make decisions about it to get some effect, right? And depending, again, on the accuracy of your model, this might be good or bad decisions in reality. And when you've got a model, right, the most important thing you want to evaluate is it valid, right? Is it actually modelling what it's supposed to be modelling? Does the system that I built this model for actually behave, at least to some degree, closely to the this model that I've built, right? So without a valid model, then the model's not helpful. The other thing is it's useful, right? So if I've got a model that will tell me the temperature 1 hour from now, it's not that useful, right? It might be super accurate to telling me the temperature 1 hour from now, but does that really help me, right? So think about what the Meteorological Bureau do. They have lots and lots of models of how temperature and the weather changes, and they want to be able to tell you things nowadays a week ahead, okay? And we know they're not going to be that accurate, but they're not that inaccurate, and particularly for the next day, they're pretty good, right? And even they'll tell you what it's like to be at every hour, even though, for example, one of the things that I know is that Melbourne is one of the worst, hardest places to predict the weather. And I only know this because I've met a few meteorologists who've come to the Bureau of Meteorology in Melbourne specifically to learn what they do here because it's one of the toughest places to go. Okay? And you can see that particularly you see it on our weather things and when they talk about these hot days when there's a change coming across. And the weather can change so rapidly with the change that if the change is half an hour delayed, everything changes, right? Like our maximum temperatures can go crazy. So it's unlike, say, Madrid, another city that I spend a lot of time in, where basically they say, okay, it's going to be 40 for the next 2 weeks. There's going to be no rain. It's going to be 40, exactly 40 for the next, maximum 40 for the next 2 weeks. And it's spot on, right? Because it's basically a desert. Nothing changes. Okay. All right. So models don't work, right? Models have built-in assumptions. And when the assumptions are wrong, or when we find out they're wrong, or when behaviour of the model actually goes outside those assumptions, they break. Yep. So there was a taxonomy theory, right, at the time in the, I guess it was the 1800s, 1800s, before the platypus was discovered. And when they found the platypus, well, first they thought it was a hoax. They thought someone had just made up an animal, sewed bits together to make up this impossible animal, right? A furred duck. Didn't make any sense whatsoever. But B, it didn't fit into their taxonomy at all. There's nowhere to put, right, this thing that lived in the water, had a duck's bill, but was furred, right? Didn't make any sense. And it's fair enough, right, because this was a monotreme, right? There's not very many monotremes in the new system, right, where we now take into account the platypus. There's not many monotremes, and they're a subclass of marsupials, which are only basically in Australia, yeah? So this taxonomy, which really wasn't prepared for Australia, didn't realise there was a whole new class of animals going on here. Right, so that taxonomy theory was broken by the discovery of new information, and so it had to be adjusted, right? New taxonomy had to be built. And models can fail when a system changes, right? So you might have a very good model for your repayments, and then the interest rate changes and actually is completely wrong, right? Because the rules have changed in some sense. Yeah. The model of how you're going to work is changed because you leave your keys in the wrong place. So it changes all your plans where it's going to go. And things get mixed up, or a book gets placed on the wrong shelf in the library, means the model, let's say the Dewey Decimal System, which is meant to model exactly where every book is no longer telling you the truth. Yeah. And so we have to know that, sometimes models aren't, well, almost always models are not complete. They're abstractions of the real world, and so they sometimes give us wrong information, or they sometimes don't work. So if you can think about in the abstract, right, so we can have a system, right, which can be in various states, right, so these dots are the various states it can be, and let's say it can transition. If it's in this state, it could transition to this state, or this state, or this state. Now, if this is the part that our model covers, right? We only cover this part and not other kinds of states and other kinds of interactions because we don't know everything about the system, but we happen to be in one of these states, and if we keep, transitioning from one place to the other, then it fits perfectly within our model, right? Because basically we can't escape from the part which is modelled by what we're talking about. So in normal behaviour, nothing unexpected happens. Everything's sitting inside this model here, right? But if we get extreme behaviour, right, so we get this kind of model, so now we could be perfectly here and then we actually take this transition out of the part that our model can deal with, right? So the actual world goes to here and can get far and far away from what we can model, and so now our model is no longer modelling what's actually going on in the real world, and therefore we get unexpected events. Right? So here's an example of that, a very challenging example of it, if you want. Right? So there'd been dozens of successful launches of the space shuttle before the Challenger blew up. You know, I guess it must have been 1987. Right? And the problem was that the space shuttle launches were in Florida, and in Florida it's always warm. It's basically tropical. So the design assumed it was warm weather. But for this particular launch, there was unseasonable cold weather. Yep. And the O-rings, which were a small part of the machine, were outside their tolerance. The seals cracked on these O-rings, and then heat from the engines escaped and overheated parts of the fuel system, and then it blew up. Right? So it shows you that, right? So NASA had made lots and lots, when they were building this rocket, they built lots and lots of models about how it worked. Yeah. And they'd done lots and lots of tests, but they never presumably simulated very cold weather on launch because it was never expected. Yeah. But then they should have thought about that before launching on that particular day. All right. So let's have a look at some simple models. So the college enrolments model, okay, is meant to be saying, okay, if we have a look, let's have a look how I do this. Control Tab. I've got to get out of this first. Let's have a look at college. Okay, so we have some data, right? So here was our enrolments in this college from 1950 to 1953. So we'll graph those here, and we'll say, well, it looks fairly straight line, right? So let's just model this as a straight line. So this is basically linear regression. We'll basically draw the best straight line we can through those points, and we say, well, actually we can work out the relationship between year, right, and number of enrolments is actually this equation. Right, that's our best straight line model. Y equals 138x minus this number here. Okay, and then we'll have a look. We'll run our model, right? From 1950, we'll run it into the future. Let's see what happens by 1960. Oh, wow, by 1960, you know, we're going to have this more than twofold increase in enrolment, right? If we look. So we were, you know, our model is pretty good at representing the real world. Okay, but is this model good? Is this model accurate? Okay, so it assumes that growth is linear, right? That's all we're doing here. We're taking the numbers and saying, what's the best straight line model that goes through our points? So there are definitely some problems if we think about trying to use this model. So what if we said, let's look at the enrolment at 1920 using this model? That seems a bit odd, right? Were there minus 3,000 people enrolled in 1920 using this model? Right? That seems unlikely. Right? Let's have a look at 1940. Right? Even from 1940, it's negative people. Right? So what if we go to the year 2000 and extend from there for a few years? Okay, 8,000 people. So, I mean, that might be valid, right? So when we make a model, we're making an assumption about how something works. Here we're making a very simple assumption, this linear relationship. Of course, we're not taking into account college enrolments. There's lots and lots of factors that are going to modify that, right? But maybe, for the purpose that we really wanted to use this model, right, which was we're planning for the college, and it's year 1953. We've just seen our enrolments go to here, and we're saying, hang on, you know, do we need to build some new buildings in order to be able to fit the students by 1956, let's say, right? So we're probably only using this model to think about 2 or 3 years ahead from now. So maybe this model is pretty good from that perspective, right? Because maybe, given nothing changes too drastically in the next few years, maybe this is exactly how enrolments will work, right? So we sort of think this steady state view that the model accurately reflects what's happened in the last few years, unless there's something different, all right? Like I don't know, a war in Korea changes things. So most of the young males are sent off to war as conscripts. And maybe that completely changes this model, and it's completely inaccurate for the years 1954, 1955, 1956, which we're actually using it for. Yeah? Yeah.
In some of our assignments, there's some that they asked us to create a model, create a linear regression model just based on time. Does it make sense to just use time as predictor for linear regression?
So you mean in this example, or you mean in the...
Generally speaking, because I saw that one in our assignment.
So, yeah. So in the assignment we've actually got... so it's more than a model. So you basically have temperature data that you're given, and it's a physics model, if you want, that says, which is not too inaccurate, that the room sort of moves to the average of the outside, moves towards the outside temperature, right? So basically that's actually true, and it depends on amount of insulation, basically, how quickly it moves, right? So the model is reasonable, right? I was giving you a very simple model because I wanted you to work on it, because actually the more interesting part of that is to build a controller, to build a temperature controller to try and keep the room at the right temperature.
Is there any real scenario that you can just predict something based on time?
On a single time point, no. But think about it. So it is true. The basic physics is correct, right? If I have a box and I sit it out, outside, then what's the temperature that box going to have? Well, it's basically going to track the outside temperature, right? Almost exactly. And what's going to be inside it. Now, there's other factors like sun hitting the box and the colour of the box. Is it reflective? So there's other factors you can take in, but actually, so there'd be sun. But if we just talk about a house, right? A normal house, then basically the outside temperature is the key driver in what's going on. I mean, if you can go into super detail. You can talk about sunlight directly hitting it. You can talk about shading effects of trees and all kinds of stuff, right? But yeah, as a baseline, I mean, remember, a model is always an abstraction, right? So just like this one is a super abstraction, right? Just saying, let's just assume, it's making the assumption, assume that all other things are equal, as they have been for the last 3 years, then we would expect our enrolments to keep growing in the same way. Because we assume that whatever growth things that are controlling growth are, if they all stay the same, then if we see this behaviour for 3 years, then maybe that's what we see for the next 3 years. And it actually could be quite good enough to be making a decision about, do we need to build a new building, right? Okay, universities go through this kind of stuff all the time. They would not be using a linear model, but they would be basically not using very sophisticated models, right? Actually, most of them won't even put a mathematical model into it, right? Nowadays, the risk-limiting approach is you ask a consultant, right, to come in and predict for you how your enrolment is going to be in the next 5 years. Now, the consultants may do complicated modelling, but in the end, they don't really present that to you. They just say, here's our numbers, right? They could do very simple modelling too, right? I mean, we've seen this in the optimisation space where, in fact, well, part of the people I've been working with, and I'll talk a little bit about a railway capacity thing where it actually was an investor saying, okay, tell me how much capacity we could run this railway at maximum without changing anything. Yeah, so this is the kind of question. You'll be amazed at what level of model the management consultant type people will do. Very, very simple models. Yeah. So people get away with very, very simple models. Of course, a simple model is easy to break, right? Just like that picture which I showed you. If you have a simple model, then you're basically making a very, very tight boundary around the world, and it may be very, very far away from where you are and may be completely wrong. Yeah? All right, let's have a look at the world population model, or a few world population models. Okay, so there's a few models to the world population, right? So different ways about thinking about world population. So you can say, all right, let's assume that the population doubles in half the time it took to double last time, right? So if it doubles in 100 years, and then the next time it doubles in 52 years, and the next time it's doubled in another 26 years, then it's doubled in another 13 years, right? So that basically takes 2 time steps, right, where we saw that the population doubled in 105 and then 52. So it seems to be doubling at twice the rate, if you want, right? So we can just extrapolate that. We can have an exponential model, so we can actually look at the population data and we can just try to fit the best exponential curve in there. So we're assuming that the population growth is exponential, right? Which makes sense in the thing. If you think about, because if I say, like, if every person reproduces 1.05 times or whatever, then that gives you this exponential growth rate, right? And then you can have a power model, which gives a slightly better fit to the data, so we can have a look at that. Right. So here's our doubling model. Right, so the danger with the doubling model, you can see, is that, okay, so here's some actual observed data, right? So 1820, population 1 billion. At 925, population 2 billion. 962, population 3 billion, 4 billion, 5 billion. Right, so there's the data we're working from. We're studying in 1987. So it all looks very good. This doubling every half a time all looks good, except till we get to the year 2030, where basically it just goes infinite, right? Because if you think about it, if you double in half the time, then as you get closer, there's a boundary basically where it just goes pew, up forever, right? This is like if I add a half plus a quarter plus an eighth plus a 16th, right? We should know that you add them up. You can add up an infinite number of those and they get to number 1. So basically, you hit a time limit and at that point you've got infinite. Right, so clearly the doubling model is not very accurate. Or it just doesn't work beyond a certain point. Because it just doesn't make any sense that we could double in a millisecond, which is what it'll say, right? Let's say after we doubled like, 100 times, then we'd be down to doubling not in 2 to the minus 100th times 105. Right, so we're going to be doubling every day or something, okay? Okay, obviously rubbish. All right, let's look at the fitted models. So here we've tried to fit the best, so here was our observed data, right? So that's all we had. And we tried to fit the best exponential curve in here, right? So we're saying, okay, y is equal to 0.9218 times e to the 0.0091x. So you can see it doesn't look like it particularly well fits, right? And that's the danger of curve fitting because, right, basically we're just having the error bars. All of the error is actually happening at the end, so we're not really hitting the end there. Here's a power model where we said, oh, let's try and fit a quadratic function between these things. Yep. And here we can see it actually is much more accurate on these points, although it's completely inaccurate. If we had any point in this line here, we will have noticed that the population did not go down, right? It's just that we're assuming that it's a quadratic relationship. Okay, so we can see how do our fitted models go, right? Then if we look at 1980, for example, how do I read this? Yeah, 4.33 billion, whereas the power model says 3.76 billion. Yeah. So they're both a bit under. Let's have a look. So we're almost at 2020 now. This says 5.69 billion. This is 5.44 billion. So we can go and check how well do these models do, right? So what's the world population? 6.916 billion. Yep. So at 2020, both of them are running under. Yep. So neither of these models are particularly good. And okay, we expect actually the exponential one is better, but the problem was because of the curve fitting which we've done here, right, which is basically assumed that this is 1, that we exactly start here, and because we get all of our error at the end, we're basically not really seeing that actually this is an exponential growth with a much higher amount. Yep. And so we can sort of go further. So let's go to time step 100. Right, well there's another problem. Okay, we get to, by 2920, this model is giving us numbers that are too big to fit in the picture. Right, so this model is clearly not true. We're not going to get to 200 billion, I doubt, right? We might make it by 2420, that's a long way away. 200 billion, there's a kind of a capacity limitation on the Earth, right? So every model has limitations, right? So this doubling model is just clearly invalid because by 2030 we go to infinite. That doesn't make any sense. These ones are better. They're obviously not as accurate. This quadratic model is clearly wrong, right? Because the population did not go down from 1820 to, let's say, 1870. Even though we don't have a data point that we've put in here, right? We know that it didn't go down, right? So it's just clearly not correct. So if we think about the physics of the system, exponential is correct, but we failed to actually accurately capture enough exponentiality there to be very accurate. Yep. So by the way, all these models are available on Moodle, and what you should be doing as part of your study or whatever is to look at them and play around with them. So let's have a look at logistic growth. Okay, I'll show you the equations for this a bit later. So logistic growth is basically like the exponential model where we assume that there's a kind of finite carrying capacity, that the environment really can't sustain more than a certain amount, right? And when we get bigger than that certain amount, then basically there's pressures that push us to go down. Because if we have no limit, then we basically are going to get an exponential population growth, right? As long as the birth rate is higher than the death rate, then there's more people producing more children, and off we go, off to infinity eventually, right, in an exponential growth rate. But the logistic population thing says, okay, we'll start with some initial population, we'll have a carrying capacity, so basically whenever we're over the carrying capacity, then we're going to force the population downwards by war or famine or starvation. Normally is the basic one that stops. I mean, we see carrying capacity kill off communities, right? If you get too many people, they cut down all the trees. So Easter Island is the great example of this, right? So this is a thriving population. They built massive stone statues, yep, and they had a thriving population on a small island. But then eventually they cut down all the trees and it became unsustainable and everyone died or left, right? Basically no one could live there anymore. So that was an example where we basically exhausted completely the resources and no one could leave. The logistic population is a bit not as bad as that. And one thing you should know is, so logistic population we can actually have a continuous formula for. So we can just type in those numbers and we can actually work out at any point, at any subtime. But in reality, we probably use a discrete model. So we probably just look at what is the rate of change and we'll just add that change, right? So we'll only look at discrete time steps. And you can see over here the difference, right, between the discrete model, which is the purple one, and the actual model. And if I start changing so let's increase the reproduction rate. So if we double the reproduction rate, so what sort of happens? So here you can see there's a kind of slope up, and it sort of reaches capacity at about 40 or something. Okay, if we double the reproduction rate, well, what happens? We slope up and we reach our capacity about 20, which makes sense, right? If we double the reproduction rate, then we're sort of going to reach the capacity twice as fast. And you can see that the discrete and the continuous models don't look that different. Okay. So what if we double the reproduction rate again? Again, you can see that we sort of reach our population in half the time, and seemingly here you can see a little bit more difference, where it's a bit more clear that it's discrete, the purple line now. So that all seems to be working. Let's double our reproduction rate again. Okay, now we start to see some problems. Well, you can see it's not so much that both the discrete and the thing are accurate with each other, right? The continuous model sort of says, okay, we rapidly reach our thing and then we stop. The discrete model, unfortunately, because we're only looking at individual time steps, keeps overshooting, then being pushed down, and then overshooting again, pushed down. And you can see it is actually getting, you know, eventually getting back to where it's meant to be, which is right at this 10,000 limit. So it's slowly getting closer to that, right? What if we increase our reproduction level again? Okay, now you can see the continuous model, remember, is just an equation worked out from the beginning, which always gives us the right answer. But simulation is what we're actually going to be doing in complicated models. And now you can see our simulation model is just going crazy all over the place, right? So, and it's wildly, so just, right? So this is a very, very important thing that we have to notice, that when we build a model, so let's say the model is perfect. Let's say our model is completely correct here. It is actually logistic regression model that is actually governing what's going on in our system, right? But we don't know, or all we can do is work out the rate of change, right? So we think, okay, for these things, then the rate of change is this, right? But we don't know the logistic regression actual full computation to be able to do it at a continuous time. Then we will get only this discrete model, because that's what the discrete model says. It says, if I look at the current state and I see all the factors at the current state, then I know that this will be the rate of change of population. So if I go for some discrete time step, then my new population will be this, right? The problem is that that's not true, because what continuous model says is, well, I go an epsilon time step, and then I recalculate and go an epsilon time step, right? Because continuous is going at the smallest possible time step. Whereas the discrete model, just being discrete, means that even though I'm doing the right thing, right, because I'm estimating now and assuming things are stable for a set of time steps, I get crazy behaviour. Right? So this is one of the things we have to be very, very careful about with simulation. So there's absolutely nothing wrong with our discrete model, in the sense that when it makes an evaluation about what the rate of change of population is, it's perfectly correct every time. Yep. But because it then says, I'll just assume that's fixed for the next time step, we get something which is way off, way off, right? Okay. Now I can make the time step smaller, right? And I'll get better. And of course, when I'm down here, when I'm down at small regression rates, right, go back to 25, then, right, really good. It's very close to exactly the same thing, right? Can hardly see a difference between those two graphs. So we have to be very aware about any time we're doing a model that we're not modelling the real thing, right? All right, so here's a challenge for you. So this is the predator-prey model, which is a fairly accurate description about what happens you've got a population of predator animals, which kill the prey animals, and a population of prey animals. Okay, so the example here are rabbits and foxes. So if we think about, so here's the equations that we think govern how these populations work over time. Right, so the number of rabbits, right, is given by this. We take the reproduction rate of the rabbits, we subtract the morbidity rate of the rabbits, and we also multiply that by the number of foxes, right? So basically, okay, this is the increase in the number of rabbits at a particular time, which is equal to given by the number of rabbits. This is the morbidity rate of the rabbits, they're just dying off, which is accelerated by the number of foxes that there are around. Right, and the foxes just goes, okay, for every fox we've got the reproduction rate of the fox, but the reproduction rate is affected by how many rabbits there are, right? Because they need the rabbits to reproduce. And then we have just the morbidity rate of the foxes. Okay, so you get this thing where basically rabbits go up, okay, because they reproduce very fast, but that means more foxes because there's more foxes can get because there's more rabbits to eat, and then if there's more foxes, then the rabbits decline in population, and that means less foxes, right? And so if you look at the kinds of things, the kinds of behaviour you get these kind of things which you can see it's kind of off phase, right? So rabbits start going up, right? But then since there are more rabbits, then a little bit behind, we get more foxes. As the foxes go up, then the rabbits start to go down. Then there's not enough rabbits to keep the foxes alive, so they start going down. So you can see this kind of varying behaviour, right? But does this look like a realistic behaviour plot of how rabbits and fox population goes? Anyone? Looks realistic? So it's realistic in the sense that if we believe our equations, it certainly fits our equations. It doesn't look realistic to me because why would the population's getting more and more different, right? Just changing over time. And in fact, you get periods where we run out of foxes. And remember that there's definitely a factor that when you get to 0 foxes, no foxes left after that. They don't sort of magically reappear, right? But if we never actually get to 0 foxes. If we have a look at this plot of the various time periods and the foxes versus things, actually we're spiralling outwards, right? We're getting more and more unstable. Okay. So we can change something. So what happens if we sort of increase the number of foxes originally? Let's make it 17 foxes originally. Yeah. Okay, so we've made a more stable system. We're still spiralling out of control. Yeah. But we started with basically a more balanced system, and it took longer, basically, for it to start spiralling out of control. So let's just drop the rabbits a little bit. Okay, that didn't help. That, in fact, made it spiral further out of control. So what's happening? Maybe our rabbits are reproducing too quickly. Let's try and reduce that a bit. Okay, no, that really did not help. That was worse. All right, you see we spiral out of control much quicker. What about we increase the rabbit reproduction rate? That also made it worse, right? So the problem with these kind of linked systems, I'm reproducing the foxes rate actually. So that was the wrong thing. Maybe let's decrease the rabbit reproduction rate. Okay, so that did make it tighter. Right, I was playing with the wrong one. So we made our rabbits not reproduce quite as rapidly, but you can still see it spiralling outwards. It's getting more and more unstable. Right? Now remember that we're not taking into account all of the effects. Right? We know that these are fairly good representatives of what happens in this predator-prey representatives, but there's lots of other factors which we're going to force, populations in the end can't grow that well. They need to have new burrows and things like that, right? And they need environment, things like that. There are other controls on population. But I challenge you actually to try and get some numbers which go down, right? Which actually get smaller. So ideally we'd like our oscillations to get smaller and smaller until we get to a steady state. That's typically what would happen in the real world, yep. 20 and 20, 20 and 20 here. Okay. Okay, so remember we definitely need more rabbits than we need foxes because of the nature of a predator, right? So we're still far out. Yeah, but we basically need to, we can play with the morbidity rates. So if we make our rabbits not last as long, maybe. Right, see, that didn't help. It shows you that even with a fairly simple system, very hard to, so I think the only thing I was able to do, no, see, even, problem is you're trying to balance things, and we only really have 6 things here, and in fact, the starting values don't make that much difference, right? We'd hope that if there is a natural sort of equilibrium, that we'd be heading towards that equilibrium. But there's no damping effects in this system. So we typically always get this spiral out, right? Getting more and more unstable. The system is more and more unstable. So I challenge you to find some stable things for the rabbit. All right, let's have a look at the Australian population. Okay, so here we're just taking some very simple kind of features into account. All right, so we'll say we had 18 million in Australia in 1995. We'll take a birth rate of 0.25, a death rate of 0.2, immigration rate of 75,000, and immigration rates of people leaving 5,000. We can see this kind of, it is exponential, okay? We are actually growing slightly faster, but it's not very accurate, I guess. So what happens, so this is an experiment many parts of Australian politics would like to do. Let's change the immigration rate to 0. All right? So what changes to our population? So it reduces. Let's have a look at birth rate in Australia. Okay, so it says that nowadays the birth rate is 12.1 births per 1,000 population. Yeah. So let's change that birth rate to be more accurate. Right, so 12.1 per 1,000. Now you can see we're actually decreasing in population. Yeah, well, it's pretty obvious. If the birth rate is smaller than the death rate, then that's right. Maybe we need to put back that immigration, 75,000. Okay, still not enough, actually. Well, let's get some other rate. Let's have a look at the death rate in Australia. .2 deaths, okay, so this death rate is wildly overstated. Yeah, so you can update that. Of course, this is the 2016 or 18 things. We update that. Okay, now we're getting population growing. Right, so let's have a look. So this, how good is this model doing? We can have a look at the population in Australia and actually compare. Okay, so 24.6 million now, but can I get a graph? Population net official site, population clock. Oh, let's have a look at this. All right, so we can see some actual numbers. How do we tick up against those? So 2014, we said 23 millions. Okay, so we're behind. Right, so what do we have to change? Maybe, so at least we think our birth rate and death rate are pretty good. I think the 18 million was pretty good for the starting point. Maybe we're having 100,000 people arrive. Yeah? Yeah, let's bring up that. Right, so ideally what we hope is that we can adjust our model and we get some of these numbers. But of course other things are changing, right? So the birth rate and the death rate. The birth rate is decreasing and the death rate is decreasing, right? Medical science is getting better and medical science is getting better. Well, birth rate is decreasing because people are having their children later, this kind of things. Right? So just over the period from 1995 to 2017, there's still a lot of things that are going on. But we could adjust this model and get fairly close to this, I would suspect. Yep. All right, last, let's look at this one. This is a very artificial model. Okay, so here we've just got that x prime, right? It's equal to a times x plus b times y plus c times z. So there's a, b and c in terms of improving x. And then y prime is equal to this times x plus this times y plus this times z. Right, so we can see for these kind of numbers, yeah, we can see that x basically sort of heads down and starts to peak up again, right? Basically because it's affected by z, right? So when z is high, it sort of gets pushed down, and then when z goes slightly negative, it starts to get pushed up slightly, right? Y, you can see, is affected mainly by x, but half by itself. So it's sort of pushed up when y is high, then it comes down to the point where basically it's almost stable. It's basically twice as much as x. Right? If we look at these numbers here. All right, so we can play around with this kinds of things. What kind of questions? Okay, how sensitive is the model to changes in the parameters? All right, so we can change. Let's say that z has twice the effect on x, twice the negative effect on x that it used to have. Right? Well, that changes the model a lot. Basically, we basically get down to this point where z has this negative effect, and of course that pushes x down way before until it gets to 0 and stops having a negative effect, right? And by that stage, everything else stayed the same. Right? So we can say, okay, what happens if y only tracks half of x? So basically, y is just sort of taking the average of x and y. Yeah. Okay, then as you'd expect, if x and y, basically y is just averaging the value between x and y, it's going to quickly become the same as x, right? Even if we give it a very different starting position. Yeah, you can see it just runs down and it's going to get the same as x. Right, and then, okay, we have this, x has this negative cycle between x and z, so x forces z to go negative, right, and z itself is just dropping off naturally. Okay, what if we give it some y benefit? Okay, so now everything's changed, right? We changed actually the interaction between the variables because now y has an effect on z. A positive effect on z, so you can see that z now, right, actually goes down slower than x. Yeah. Y plummets down towards x, actually overshoots it, comes back up. Right, so even in this tiny simple series, basically this is, if you want, this is just a matrix multiplication where I have this matrix here of x, y, this is this cross product matrix. I start with this initial value, 1, 2, 1. I just multiply by that matrix, multiply by that matrix, multiply that matrix again. And I can get this kind of behaviours. And I can go the other way, right? So if I make the numbers a bit different, put some big numbers in here. So here we're getting a very convergent behaviour, right? If I just make, yep, I can get divergent behaviour as well, where the numbers grow off to infinity in different directions. All right. So I recommend that you take those spreadsheet models and have a play around with them yourself. Let's have a 10-minute break and we'll come back to part 2. So we'll meet at, well, let's say 10 past 10. Restart at 10 past 10. Meanwhile, you can ask me questions. Yep. Yep.
In the Java app, we can't copy the data.
No, so in the first...
The first you can't copy that.
Yeah, no, so the first one you can copy. You can grab the whole data and extract it out. Well, you can in Mac. The simple Weasel demo, you should be able to grab the output and then you can write a little script to process it. Otherwise, you can just do a few experiments, just look at the thing and count it yourself, right? It's not too difficult to count how correct it is. That's in the worst case. I agree in the genetic algorithms case, then you basically have to run it and let's say stop it at every 25 or approximately every 25 operations, or you can actually single step it for 25 operations, record the, let's say, the best fitness and the average fitness at every time and do experiments like that. Yep.
Almost like the meaning of the GA algorithms has different interpretation in other websites. It's like, and in the website providing there are some parameters that you didn't explain, like what actually the selection rate does and what actually how is the best.
Okay, so there is now I wonder if I can. There is some description if you go to the thing about what the different crossover methods are. So I think for the project you can experiment with them, but I think you'll find that for this very simple simulation that we're doing, basically they don't make very much difference. The big difference is the mutation rate. That makes a huge difference, right?
They have something called selection rate, but they didn't explain.
So this selection weight is about biasing how many of the good ones you select. So in genetic algorithms, right, you have to pick, you try to pick the best ones from the previous generation to reproduce, right, to do some crossover with them. So the groups of best ones you pick, they do crossover and then you go forward. But typically you don't just pick the very best one, right, or the very equal best ones and cross over those, because that is unlikely. Well, you think that some of the populations which aren't the best ones may have some very good bits in them. So this selection thing will be about how many, or what's this, how do you bias the coin? Effectively, you're flipping a coin saying, okay, I'm going to pick the best one or the next best one with some probability, or the next best or next best. So basically some bias selection where you're trying to keep better ones than worse ones.
I'm curious because according to my observation, they always pick the best one, and they didn't give explanation in detail. It's like
Okay, so I don't know exactly what's happening in the VLab.
that's why I want to ask because I'm planning to implement the course by myself, and
Right.
people have different interpretation in the open sources, so that's why I'm asking whether.
Yeah. So that is the problem. I mean, GAs mean a lot of different things, and there's a lot of things. So, okay. So yeah, I probably can't. Or maybe I can bring up the VLab thing because I haven't enrolled.
They make some different changes, but they didn't really specify the exact changes they made.
That it? It's intro tech. Yeah, this is a problem because I haven't. Okay. So hopefully I can look at least the information. Oh, here, right? So you want to play with them? You can play with them there. But if we go to the GA, okay, selection. Right, so really well selection, that's the one I was thinking about, is proportional to its fitness. So that's the normal one. So basically you say, okay, if I have 5 of them and one's worth 1 and 2 and 3 and 4 and 5, right, then the top one, which is 5 out of a total of 15 fitness, I'm going to select 1/3 of the time, right? And the bottom one, which is 1 out of 15, I'm going to select 1/15 of the time. So that's a normal selection, the selection rate, right?
No, in the demo they
Yeah, so okay. Elitism is the best strings are copied directly through so that they stay unchanged, and then the rest of the population is filled using the normal approach, right? Does that make sense to you? So elitism just says, let's keep the best one. Ranking, so then you, basically this is slightly different. So then you say, okay, I sort them by rank, and then I just give them a proportion to their rank, right? So that means, that's exactly like the 1, 2, 3, 4, 5. So the highest ranked one gets a 5 out of, if there's 5 candidates, it's 5 out of 15% chance, which is different because it might be only slightly better than the other ones, right? There's just ways of building the selection criteria. I think the information is there. It's a little obscure.
You know, it's not detailed.
All right?
It's like, if you always pick the best fitness, what if they have...
But you don't always pick the best fitness. None of these do that.
For the last options.
No, but elitism isn't... Elitism just says this. It says the best one goes through unchanged.
Yeah, it means best.
But the rest are produced using the same, using one of the ones above.
So, for instance, because it mentions the best strings, what are the, like, it can be best 2 strings or all the best strings.
Yeah, okay.
In case they have all equal
So-
fitness, so it will...
If they have all equal fitness, I think, well, you can have a look at what it's doing, but I suspect it means that all of the equal fitness ones, because remember they're marked in red, I suspect they all go through unchanged.
Right, if they're copied directly to the next generation.
The only way, the only way it can converge is if all of the strings are best, in which case then nothing gets to change.
All of them have 0 fitness, and they are all copied to the next generations directly without any mutations, so they won't convert.
No, but there is mutation, right? So there's always
I don't know,
mutation.
it mentioned copying to the next generation directly.
No, but I think mutation was always applied afterwards.
I don't know, that's why people are doing it in different ways.
Yes.
The website.
See, after an offspring has been determined, it undergoes mutation. So I think, so if you're using elitism, you have to mutate the elites as well.
Yeah,
Right.
that's what I'm asking. We can just implement the...
If you implement something and it's reasonably close, then obviously, but you need to add in your implementation, and maybe you should also do a little demonstration about why you are close to this one. So at least do one experiment where you actually use the app and show that you look to be similar, right? Or similar enough. Yeah.
Can we use different code to generate the simulation?
Yes, if you want to write your own genetic algorithm simulation, but as I'm saying, you want it to be as close to theirs as possible. I think there is enough information, pretty much. I agree that always there's some slight, right? If you don't have the code in front of you, you don't know exactly what they're doing, but assume that they do mutation after they do crossover. That's what they say. But that also means that if they do elitism, that is that someone gets to go through straight away, then they also get mutated afterwards. And that's probably checkable by looking at what's happening, right? Change the mutation rate to 0, and you should actually get behaviour where it just stops, it gets stuck at 0, right? Because the elites get copied, everything's elite because they're all equally bad, unless one of them's lucky and has something correct in the very first iteration.
Is the app provided in the lab restrict your parameters have to be like more than 2.6, so you can always kind of text by your phone.
Right. Yeah, so you can't do everything. Sorry, did I answer your question?
I have a different code to simulate exactly like the wisdom.
Mm-hmm.
And I use that. I have asked in the forum. You can have
So I think as long as you are, you've done some steps to show that your code is doing the same kind of GA as them, or close, or is close to that. So at least do one thing where you actually say, you show the side-by-side running. Right? It shouldn't make that much difference. Well, oh, we've gone past the start time. in our question time. Let's get on. Okay, let's talk about simulation. So we're trying to model something that models emulating processes. So far we've seen simulations in a very simple sense, right? Where we just had very simple equations. We're trying to mimic relevant features, and in reality, simulations are very big and very complex area, and they're extensively used in lots of things, right? So we do emergency training exercises on simulation. Pilot does, you can actually get completely licensed now only flying in flight simulators. Why? Because the flight simulators are so accurate, right? Effectively, many of them are running the same software as the actual plane, right? And then we know, and the accuracy of modelling how plane behaviour works in weather is very, very accurate. Of course, they're not exactly the same, right? But you can actually get fully licensed, I believe, in flight simulators nowadays. And we've seen the simple simulations like logistic growth. And of course, we're in computer science, so our simulations for us are not an equation, but actually a computer program, right? And the nice thing about a simulation is it's explicit. It basically forces you to write down exactly what's going on. Okay? So here was the logistic growth function that we saw. Right, so you have this is basically the population here, the starting population, the carrying capacity, and then here's the rate of expansion, and you can see time in there. Right, so that's the actual formula, which will give you this nice smooth curve starting from the starting population and reaching the carrying capacity eventually, assuming the rate of growth is positive. Right? So behind it has this underlying formula. So that basically this is the rate of increase, right? Is the growth rate times the current number times 1 minus n divided by k, which is the effect of the carrying capacity. Yep. And so that's exactly right. And when I was talking about the simulation using the exact growth rate, that's exactly what I was doing. It was just calculating the growth rate at this particular time and then multiplying by time to get the new number of people, right? So if we have 10,000 growth rate, 10,000 people, right, 0.01 is the population growth, then this is 1 minus 10 over the 500,000 carrying capacity, then we expect 98 new population in one more step. Yep, so our population moves to 10,098. So we start our climb up. But as we saw, right, when we do simulation, when we're not doing this continuous time and re-evaluating this growth rate at every time, but just taking a step, assuming the growth rate stays stable, then we can get this kind of behaviour. Okay, if we take very small steps, we can get this thing which looks perfectly good, right? The simulation is perfectly as good. But if we then take larger steps, we can get this kind of thing, right, where we cycle, right, or we can be gradually getting more small and small. We saw that example. You can also get gradually getting larger and larger. And then as you get this value of r higher and higher, then you just get to chaos, right? Because basically the time step is too great and you're way off what's going on, and actually it's not simulating the system at all, right? So this is not really simulating the system, but it's at least trying to get back to where it's right with the system. But once the value of r, this reproduction rate, gets too high, then we just get rubbish, basically. So we have to be careful, right? Complex systems are unpredictable. And so if we have this, so here, remember, we're actually using the exact growth rate, right? There's nothing wrong with our simulation in terms of that. It was only that we're using a fixed step size and assuming the growth rate stayed the same over that step size that we got something wrong. And the problem is nonlinear formula are often like that, right? So it's very unlikely, for example, that in this regression we can actually get a closed form formula which actually tells us the answer at every point, right? So we're typically in a simulation going to have to do this time-wise, stepwise interaction. But there are advantages to simulation. So you can interact with the simulation, Simulations can take account of non-numerical features, right? So far we've just been talking about numbers, but in the real world, simulation's very important, and we take account of a whole lot of yes-no decisions, right? And they allow virtual experiments and lots of these studies in real life. So if I get time, I'll tell you about control, modern control. How is your engine controlled in a modern car? And interestingly, they use simulation to do that. And they do that because that gives them the best behaviour, even though there's a whole lot of non-linear, continuous things going on. Okay, so simulation is often a major project, right? Because we're trying to capture a complex system in enough detail that we get believable or usable results. And part of that is not just that, it's actually, we've got to be able to present the results to the user in a way that makes sense, right? So we have to implement the model. So first of all, we have to basically understand what we believe the rules are of the simulation and what parts of that, the system that we're looking at, we want to actually model. We very importantly have to source some data, right? Because we're going to need to know, like birth rates and death rates or whatever. We're going to need to understand that and find the data that builds that, right? That tells us what are the right values for these kind of parameters. We typically need some kind of visualization because we're going to do what-if experiments, so we need to be able to explain to the user who's doing those experiments what the changes are, what results, right? Just like our little graphs in the Excel spreadsheets. And a user interface so that we can actually, they can change those things and see the results. And finally, this calibration and validation. So we need to actually run our simulation many, many times and compare it with the system that we actually know that we've got collected real data from and see that it actually behaves like that real data, right? Ideally very, very closely like that. Yeah?
How do you want to just measure whether they react like each other or not?
So if it's something like a population model, right, then I'm basically going to talk about error. So what is the error of the population at every stage? If I see that my my model models all of the data I've seen, so I'll train it on, let's say, I'll start the model from the years 1900 to 1950, and I'll see, okay, how well does it do on the data after that? The usual test and training separation. That's a very simple example where we're going to have one number, right? The tricky thing is, let's say we're doing a simulation here of tree plantation growth, yeah? So then what we're going to do is we're going to take some measurements we found for, say, density wood over a few hectares, and we'll look at what our simulation says, and we'll see that, let's say, are key numbers, the key features that we're really interested in, that we're getting good-looking values on that, right? Or maybe we see that actually the spread of the different trees is completely actually different, obviously, because there's randomness going on anyway, but like the balance, if we look over the entire population of the trees in this simulation, then our numbers are pretty close to what we saw in real life, right? So it's basically judging what it means to be accurate is also about what are you going to use the simulation for, right? You want it to be accurate to be able to answer the questions that you want to answer. So it doesn't, if you want it to be that, okay, this exactly tells me where the Pinus radiata are, because they're the ones I need to cut down, right? So what I need to know is where they are. Then I'm going to look at it. I'm going to look at my simulation of the trees, the different tree patterns. I'm going to say, okay, mine says that they're here. In the real world, they're there, so it's wrong. Whereas I might have exactly the right balance if I count up the total number of pine trees and the total number of ash trees. Then mine exactly right with respect to reality, but I wanted a different thing. I wanted to tell me where they were going to be. So it has to simulate that correctly, right? So it's part about what you're going to use the simulation for. So in fact, because simulation is a very important thing, there are simulation toolkits which allow you to build simulations rapidly, okay? And indeed, they have some of these other parts, like user interface parts built in, right? So you can build the user interface rapidly. Actually, building user interfaces rapidly is just a generic thing that lots of applications need. Yep. So here we might have a simulator for virtual growth of plants. And so you can see, okay, here's a model which sort of showing how plants grow, right, over time. And at some point they reach a point where they can bud and produce flowers, etc. Right? So you can have rule-based models, so it's the kind of things that are used for plant growth or tree growth. And tree growth is very interesting because people want to model tree growth when they're working out how do I build my plantation? Like how close do I put the trees together? Because they shade each other, right? So obviously the more trees I have closer together, then the more wood I get. So it sounds great, but it's not true, right? Because there's some maximum closeness, in which case they start to shade each other and basically they stop each other from growing. So you need a model of growth, and you can these kind of patterns, right? This says, if you see an X, you can replace it by this pattern, F of A, F, B, Y. So in one step we get this. So you can sort of see it's like a fork off of type A. And then A gets replaced by X, and Y gets replaced by this Y here, gets replaced by a fork the other way. Right, so you fork this way, then fork that way, then fork this way, then fork that way. And then you can see each individual tree branch looks similar, right? You fork this way, then fork that way. So it's a recursive kind of view, which tends to be true about plant growth. Obviously it's not exactly like this, but it gives you, if you look at pictures that you get out of these kind of tree growth models, like they don't, well, those ones maybe not, but it looks reasonably like a tree, right? Of course, these perfected models are not exactly the same, and obviously there's some randomization going on here because it's not perfectly symmetric. Yeah, but it allows you to build up some rules for how. So you're basically tossing a coin to see whether you extend the B into the Y or not, or leave it. And in fact, we have one of the world's experts on this kind of simulation of life, virtual life, John McCormack, in the department. And he can produce fascinating pictures of life, which look very realistic, by using these kind of simulation approaches. Yeah, yeah, and as I was talking about, so if you think about these pine trees, they do have this kind of behaviour, right, of growth. And you can work out how they interact, right? How much they shade each other, and then you can work out what actually happens in terms of how much trunk growth you get. Yeah. So you can work out how close should you put these trees to get maximum amount of basically wood produced per year. That's typically what someone who's building a plantation wants. Yep.
So interesting, because it's exactly the same case that I have in my thesis. So again, here, for example, you have two trees, and you can compare them from different points of view. For example, some size of their, I don't know, leaves or something like that.
Yeah.
And then in some aspects, the difference is much more important. For example, if the size of leaves are different, it is more important in comparison to the situation that trunk is not, for example.
Yeah. Yeah.
So if there are a bunch of different, I don't know, features for one, for example, tree, and you have 900 trees.
Yeah.
So deduction seems to be a bit more weird to, I don't know, make a decision whether the simulation works fine or not. Especially in this case that some of the features have more weight in comparison to others. Is there any sensible way to just make a decision about whether this simulation in this situation is good or not?
Yeah, so, I mean, the only thing you can really do is you can say, here's a question that I want to answer, right? And then I can look at the real world data and answer that question, and then I can run my simulation with the same start positions, or trying to simulate that real world scenario, and then answer the question from the simulated data. Okay, my simulation is accurate enough if I basically can get an answer from that real world, from the simulation, which matches to some degree, right, the real world data. If I have lots of real world data, I can split it into test sets and training sets, right, build my model from my training set, and then test on the test set, because I've got to be careful that I don't just make my simulation work exactly correctly on the training data and then test on the training data, and then obviously I should get good results, even though they won't be perfect, right? So it ends up being the same, like any kind of machine learning problem. But a simulation is harder because basically you often don't have this, like a training system which is going to drive you, like a machine learning model like linear regression or whatever. It's going to drive you to get the right parameters. But you can train like the parameters of your simulation, for example.
What problem is exactly detecting, I don't know, how should they detect whether some differences make sense or not, especially when one of my features have more weight in comparison to other features?
So the point is that you can only test it by actually looking at the simulation on the questions you want to answer, right? Basically, because you're building the simulation for a purpose, right? So if my purpose is I want to know absolute amount of wood weight that I get in 10 years from now in my tree simulation, then I don't really care if like the branches go out too far, right? And it's actually way wrong what actually happens. But if I get the right wood weight because I'm taking into account shade enough and blah, blah, and interaction enough correctly that even though the pictures of my trees look terrible, right, the wood weight is always spot on, perfect. I don't really care, right? It's the purpose of the simulation. Yeah. So one advantage of simulations is we can do these virtual experiments. Okay, so we can release a deadly virus and we can see how much population gets killed off. Probably don't want to do that in real life. Yeah. We can burn the Mona Lisa. Why we want to know what burning the Mona Lisa looks like, that's a good question, but we can do it. Obviously, we're not going to do that in real life. And I guess this is the thing, right? The simulation is for these what-ifs. The simulation is meant to not just simulate reality, right? We're going to use it to ask questions about if we change some things. So that's another important point, that the prediction, right? So you can be just predicting what's future of the system. That's often very hard. Or you can say, if I change this parameter, what would happen to the system, right? So if I'm doing modelling traffic flow, I want to say, okay, if I change, for example, our freeway, so we have these red lights, right? So that when you enter, you have to stop and cars can only enter at one at a time at every red light. How does that change traffic flow? Right? So in fact, they did simulations of that and showed that that can really improve traffic flow. Seems very strange, right? We just stop people getting into the freeway as fast as they could, and it improves traffic flow for everyone. So it allows us to do things like plan for the worst case. Right, so if we have a bushfire simulation, that's a critical thing in Victoria, one of the worst bushfire places in the world. Right? And there are lots and lots of bushfire simulators out there. If we simulate what happens if a cigarette's dropped from a passing car, okay, there's the fire. If we have high wind, what happened? Well, high wind, right, drives that simulation so that the spread is much, much faster. So what if we had put in a fire break, right? So imagine we already had a fire break here in the high wind situation. What happened? Well, in this case, we can see it wasn't good enough, right? The fire break helped protect this space, but then basically the fire escaped across here. So if we're thinking about, we're at this situation now, right? And there's high wind and we're saying, well, should we build a fire break across here? We can say, well, okay, no, that's not good enough. We need to build a fire break here as well, for example. Okay, what if we had done fire reduction, burning, beforehand, right? What would the fire look like then? You can see, oh, well, with reduced fuel load, you know, we have much less spread of fire. So it allows us, and we play this difficult game in Victoria, which is every time we do fuel reduction burning, of course, we could start a fire that gets out of control. So there's always a fight. We can, look at scenarios. So here's starfish, crown of thorn starfish on Davies Reef, and if we assume that they seek out the coral, which is probably pretty likely, they're not unintelligent creatures, then how do they spread? If they just do a random walk, okay, they spread much further. So we can build different simulations of how the starfish behaviour, and we can compare that with real life and understand starfish behaviour. Another thing, and you've seen this in the examples we played with, is that we can test how changing parameter values changes the outcomes, right? And we can have these kind of two kind of examples. C, right? C is the sort of long-term trend. So C says, okay, if it's less than 0, we're going to gradually decrease. If it's equal to 0, we're going to stay the same. If it's greater than 0, we're going to gradually increase. And K is the damping force or the oscillation force. Right, so if it's less than 1, then we're gradually damping lower and lower and lower, which is what we'd like to get to a steady state simulation. If it's 1, then we stay in the same sort of oscillation, whatever happens. And if it's greater than 1, then the oscillations get bigger and bigger, right, like we saw in the predator-prey. So C is like, so this is kind of abstract simulation, right? It's not actually taking a real one, but just talking about factors that you see in simulation. So you can see a kind of trend rate, right, which you can measure. Is the trend down? Is it stable? Is it up? And then we have an oscillation sort of, or a damping. Are oscillations getting smaller? We'd expect in any real-world system that things would tend towards an equilibrium and get smaller and smaller, but maybe not. And if we saw in our predator-prey example, right, that basically we could not pick parameters where we didn't get less increasing oscillation rate. Yeah. So here we're just doing a kind of abstract model, but you saw those kind of things happen. So this, you can look at the output and you can decide what are we seeing in terms of this damping or non-damping or growth, or, you know, is it decreasing over time or is it increasing over time? So we can use virtual reality to do simulations, right? So nowadays, when people design an apartment building, they always build a virtual reality model, right? And they have the customers walk through the entire thing before they ever build anything, right? Because people can get a feeling for what's going on. Architects love this idea that they can show you what they've built without actually having to build the millions of dollars involved. And SensiLab has lots of examples of sort of 3D modelling, where we use 3D modelling to visualise something, and we can then simulate it and have a look at it. And I recommend you go and have a look at some of these. So Smart Forest is exactly this kind of thing, about building a virtual landscape, sort of working out, if we look at the underlying soil types, right, how do trees grow over time? How do they spread? All right, so let's talk about optimisation briefly. So in a simulation, right, you basically have to make the decisions that are happening in that simulation, right? So models, remember, are not just for simulation. A simulation model says, well, here's something which we think is working and let's follow it through. But typically, if we have to make decisions within those processes, they're fixed or they're decided by some policy. Right? I'll give an example in a moment. And sometimes that really gives you a really bad simulation, right? Because you have to make decisions which about what's happening. So if you think about, if we're trying to decide about traffic patterns in Melbourne, right? Then we basically have to make a decision for each individual trip. What's the route that that car would take? Okay, so in that case, we would typically go something like, oh, they take the shortest route, yeah, which might seem valid, but actually it's not really valid, because what happens is then all the cars are on the same routes and then they get clogged and then they're really, really slow, and people then learn to go a different way, right? So you need to be able to make decisions which mimic reality. And so optimization models work in a different way. So they say, okay, we're just going to let the optimizer make those decisions for us of our model, and we're going to just add constraints about the system, and then let the optimization work out what's the best decisions, and that can better reflect the true behaviour of the system. So here's an example, which I talked about briefly before. So we've got a train network, and we want to decide what's the total capacity of the network. How many trains could it run a day? So I might be an investment company deciding whether I want to invest in this train network. And if I do, then I want to know, okay, how many trains could it run a day at total capacity? And let's say, what are the bottlenecks and how much money would I have to spend to increase the capacity if I needed to, right? So a simulation model would emulate all the kinds of rules of the network. So what's the minimum distance we can have between trains? And it would greedily schedule the trains. We'd sort of start sending out trains as quickly as we could, as soon as we could. But since we greedily schedule, we actually can stuff up things, right? Because you can say, start putting a train down this one-way track here, and that'll stop another train coming this way for a long, long time. And if we'd waited a little bit, maybe this train could have got through before that train arrived, and actually we could get more throughput in our system, right? So an optimization model works a different way. It says, okay, let's just encode the network constraints, saying if you've got a one-way track, you can only have one train going one way at one time. And then we'll just say, let's ask the optimizer to try and schedule as many trains as possible, right? So it's making the decisions about when the trains run in order to make as many trains run as possible in order to answer the question that we're interested in, which is what's the total capacity that we can run this train network at, right? And so optimization gives you a different approach to this, okay? So optimization modelling is usually quite different from simulation modelling. So simulation modelling, you typically write procedural code. We have a simulation library, which is procedural in itself, because we're basically saying, well, this happens, and then this happens, and then this happens, right? And the problem is that we make lots of greedy decisions in our train example. We make lots of decisions like, okay, now this train can go, it goes, right? And now it's gone, and it's basically taking its track for wherever it's going. In optimization modelling, we're going to capture the rules of the system by constraints, and then we have to express those constraints in a way that a solver can understand them, right? And we can do that in high-level modelling languages, and that allows us to express optimization models succinctly and even use multiple different solvers to tackle the same problem. And since I developed Musinc, strangely enough, that's an example. Okay. So here I want you to think a bit. So here's a very simple simulation I might want to do, or model I want to build. So I'm talking about a narrow heads, right, where ships have to go through and they need tugs to move them through, like Port Phillip Heads, for example. So each of the ships needs to enter or leave the channel, right, and it has a channel travel time, so how long it'll take to cross the channel, and a direction of travel. It's either going in or out of the port. And each ship may need some number of tugs to move it, okay? So really big ships need lots of tugs. And it's also got some requirements about when it's got to go. So it's an earliest time which could actually go, so it's got to be loaded, it's got to be ready to go, for example, right? Or it's got to arrive from wherever it's coming. And there's a latest time by which it has to start this process. Yeah, because it needs to get somewhere. So the question is, how many tugs do we need to ensure that no ship is delayed, so every ship moves within its earliest and latest start time? And the question is that we have to actually make this decision, right? The actual time we schedule a ship is not actually fixed, right? That's part of the decision of the process, and that's going to affect how many tugs we need. All right, so here we go. Here's a question for you. Here's some 5 ships, okay? A and B are going in, right? C, D, and E are going out. And here's the data for them. Estimated start time, so earliest start time, latest start time, the travel time, and the number of tugs they need. How many tugs can you use to get all those ships through in time? And I'll give you a hint. Well, you need more than you need at least 2, right? Because some of the ships need 2. And if you have 8 tugs, for sure you can do it, because there's only a total of 8 tugs needed for everything, right? So what you're meant to answer is, okay, how many tugs do I need? What's the minimum number of tugs I need to get all those ships through in that time? 2? You say 2. It's a minimum, but is it enough? Ah, see, that's the point. So you can try by building a simulation, right? So a simulation would say something like, okay, let's just take the ship A, they can go first because they got the earliest possible start time. So let's run them at their earliest start time, right? So from 600 to 900, they're going this way. Yep. And D, well, D can go at 800, but hang on, if it goes at 800, it's going to hit, right? Because they go in the opposite directions. So it's going to have to wait till at least 910. So we've got to wait 10 minutes until the A leaves. So 910, we could move D this way. Yep. And it would be out, right? It starts at 910 and it takes 500, so it'd be out by 1410. Okay. So who's next to go? At 1300, right, we could move E this way. Even though D's still moving that way, they're moving the same way, so they don't have to be far apart, right? So at 1300, we could have E come back this way. Yep. And then at 1500, well, at 1500 we can't go that way because remember, if this guy goes at 1300, he's 1700, he's still going that way. We have to wait to at least 1710 to get B to go the other way, right? So the question is, how many tugs do you think we need? What I want you to do is do your best possible simulation, but given we're running out of time, I'll just go for a guess. Someone said 2? No? I gave you a guide between 2 and 8. 4? 5? Yeah. So, well, let's have a go. I'll show you how to. I'll show you a optimization model. Okay. So we're going to have n ships, right? For each ship, we need to know the number of tugs it has. This is just the data. Okay, we've got a safety distance, which was 10 minutes. Basically, 10 minutes, we have to keep them apart so they don't run into each other. The earliest start time, the latest start time, the travel time it takes, and whether they're going inwards or outwards, right? So now we're just calculating. So the only times we're interested, the only medieval times, we take the minimum earliest start time. That's when the whole process can start, right? No one's starting before that. So that's the start time of the whole thing. And what's the latest time? Well, if we take the latest start time of any ship and its travel time, right, that's the latest time that would ever be interesting, because that was when one ship, the last ship possibly, leaves the whole channel, right? So these are the only times of interest. Okay. And then our critical decision is, for every ship, what time does it depart? Yep. So that's the decisions that we need to make. And for every ship, we want that the time it departs is greater than or equal to its earliest start time, and its time it departs is less than or equal to its latest start time. That's just the constraints of the game, right? Those were the rules. Okay, and the tricky part is the other part, right? We've got to make sure that they don't hit. Yeah, they don't go through the channel at the same time. So we're going to do some other decisions. We're going to basically think for every ship, there's going to be a next ship, the one that goes after it. Right, so basically we're ordering the ships through the channel. Yep. So every ship is a next ship, except the last ship, which has a next ship of 0, right? So there's no next ship after the last ship. So for every ship we assign a next ship, except it could be 0. And then we know that they all have to be different, right? If 5 is the next shift after me, it can't be the next shift after anyone else, right? So the next ships are all different. So that's making sure that every ship is followed by a different ship. Okay. And then here's the complicated part of, which is talking about the interaction of the ships. And we only have to, the nice thing is now we've got the next ship after us, we only have to talk about our interaction with the next ship. So let's think about the two cases. If we are going in the same direction as our next ship, right, that means we're heading in the same direction, we can be really close, right? We basically know that the time that our next ship can leave is just the time that we leave plus the safety distance, right? It just has to be bigger than that, right? Because we're heading in the same direction. But we have to be careful, right? Because the travel times are different. We can't have the next ship, imagine that we were left really close to each other, but the next ship is faster than us. Then actually the next ship actually hits us from behind. So we also have to check at the end. So if we look at the time that the next ship left and its travel time, that has to be greater than the time that we left plus our travel time plus the safety distance. So that's making sure that we don't get hit before we hit the end. Okay? Other case is that the next ship and us go in opposite directions. Right? That means we have to basically finish before the next ship can start. So if we take the time of our start, we're at our travel time, so that's when we hit the other end of the channel, and we had some safety distance, then that's the time that the next ship can start. Right? So this is modelling how the channel behaves for these two kinds of behaviours. Right? If we're going the same direction, we can go very close. If we're going in opposite directions, then basically they have to wait until we've completely finished. And then we've got the real decision we're trying to make, which is how many tugs do we need, right? Now, luckily, we have a complicated global constraint which actually does exactly this counting. It says, if these are the start times of some jobs, some tasks, and these are the durations of those tasks, which is the travel time, and this is the resource usage of each of those tasks, then this counts the maximum number of resources we ever need at one time, which is exactly counting basically how many tugs we ever used at one time. Right? And now we're just going to minimise the number of tugs. We're going to ask the solver, solve this minimising the number of tugs, because that's what we want to know. How do we do this with the least number of tugs? All right, and we can run this. We run it on channel 2, which was the data I showed you. I've got a little, I need to... How do I move this up? That's what I want to do. So you can see we can manage to do it with 3 tugs, and I showed a little demo. So basically, there's ship 1 going first, then ship 2 actually goes last. Ship 3, right? These are basically is heading in the thing this way, but it's going backwards. You can see these 3 ships are all sort of co-using the channel at the same time to fit within their boundaries. Okay, you can see that's different. The first solution we found, well, the first solution had 8 tugs, right? Just try to run them all the same time, and we found better and better solutions until we eventually found a 3-tug solution. Okay? So I challenge you to work out that 3-tug solution is quite tricky. And if we run a different data set, okay, so here I've just changed a few of the end and start times and nothing else about the data. So if I run with that, so in this case it turns out I can't do better than 5 tugs. Basically I'm forced to run all of these 3 ships that run backwards at the same time, so they need 5 ships. Right, you can see they're very close together though, because the times are close. Right. So this is meant to illustrate why we might be interested in doing optimization models, because sometimes within our simulation we may need to make decisions. If we only make those decisions greedily or use some fixed policy, we can actually miss the whole point of the simulation. Right? So it's harder to build optimization models than simulation models, and they don't run as efficiently as simulation models. Or at least it requires more expertise to make them run. So the good thing is that they don't rely on these greedy choices, and it can directly answer these kind of questions, okay? So simulation models would often require trial and error. If we tried the same thing as a simulation model, we could say, okay, let's give it 2 tugs and see what we can do. Do a simulation with 2 tugs, and we find, oh, we can't schedule. If we do it with 3 tugs, we'd probably also find we couldn't schedule it, because any greedy schedule is probably going to get it wrong. Right, so the simulation model might find, okay, there's a solution with 5 tugs, right, where it's actually wrong. There's a solution with 3 tugs, we just didn't actually answer the question properly. Yeah? So simulation can do a lot more wide things, but optimization can answer more complicated questions. Okay, so there's lots of demonstrations you can find in the e-research centre, in the virtual laboratory. There's virtual reality examples over the world, social research methods, and I guess if you want to look at optimization models, you can look at the Minizinc page. Questions?
I have questions.
Yeah.
If I were going to build a fire spreading over the forest fire,
Yeah.
which I'm going to do
Yeah.
in the summer, then the number of the fire spreads will depend on certain things. For example, like the fuel, the woods, materials, for example, snow, and then the water, you know, the rainwater level, the weather, and also carbon peaks, competition, for example, and then the river, something like that. So you're going to have to take into account all things together. You may use simulations based on that for example, like from one kind of things, and it's going to spread randomly, so not going to be like a circle. How would I do that? The question's
Okay, so basically you're going to, first of all, you're going to do a finite element model. You're going to basically break up the space into like, I don't know, what level? Meters or 10 meter squares. And you're basically going to say, we assume the state of this 10 meter square is one thing, burning, you know, or it has a burning, intensely burning,